In the previous presentation, we had discussion on the series combination of resistors. Now in this presentation, we will be exploring that how an electrical power is delivered or absorbed in the series combination of resistors. So basically, electrical power for any system is obeying the law of conservation of energy, which states that the energy cannot be created nor destroyed. So the same case is for the electrical power, which states that the power delivered to any system is equals to the power absorbed by the system, or simply we can say that the sum of all the power delivered or absorbed to the system is equals to 0. So the sum of all the power, let's say PT, total power, delivered or absorbed by the system is equals to 0. Or simply we can say that the sum of all the power delivered to the system plus the sum of all the powers absorbed by the system is equals to 0. Now to understand this point in a more brief way, let's take an example in which we have a DC voltage source which is connected in series with three resistors R1, R2 and R3. And E is the potential difference across the terminals of this DC voltage source. And let's say V1 is the voltage drop across the first resistor, V2 is the voltage drop across the second resistor, and V3 is the voltage drop across the third resistor. And for a series combination of resistors, we know that the current is the same through each point in the circuit. And here we have a conventional current from the positive terminal of this DC voltage source towards the negative terminal of this DC voltage source. And we already derived formula for an electrical power, which is P is equals to I into E, where I is the current in the system and E is the voltage or the potential difference of the component. So we already discussed in the video lecture of electrical power that whenever a current is entering at the negative side and leaving the positive side, so the power of that component is negative and that component is used to deliver the power. And whenever the current is entering at the positive side of any component and leaving the negative side of any component, then at that case the power of that component would be positive. And by positive power we means that this component is used to absorb the power or consume the power. Now we already discussed that the total power for any system is equals to 0. So in this case, let's say the power of this DC voltage source is PE plus the power of this first component is, let's say, P1 plus the power of this second component is P2 plus the power of this third component is, let's say, P3, which is equals to 0. Now for this voltage source, the current is entering at the negative side and leaving the positive side, so the current in this case is negative. So the power in this case is minus Is into E plus, for this case the current is entering at the positive side and leaving the negative side, so the power in this case is positive. So we can write down this as a Is into V1 plus, in case of R2, the power is also positive because the current is entering at the positive side and leaving the negative side, so the current in this case is positive, into V2 plus the same case is for R3, Is into V3 equals to 0. Now move this term into the other side of equation, we get Is into V1 plus Is into V2 plus Is into V3 is equals to Is into E. So this term is basically the total power absorbed by the system equals to, and this term represents the total power delivered by the system. So from this we derived that the total power absorbed by these three components is equals to the total power delivered by this DC voltage source. Now to understand this in a more brief way, let's take another example in which we have a DC voltage source which is connected in series with three resistors R1, R2 and R3. and R1 resistors having a resistance value of 1 kilo ohm, and R2 is having a value of 3 kilo ohm, and R3 is having a value of 2 kilo ohm. And there is a current 4 milliampere in this circuit from the positive terminal of this DC voltage source towards the negative terminal of this DC voltage source. So we already proved that the sum of power absorbed by the system is equals to the sum of all the power delivered to the system. First of all, we will find out that how much power is delivered to this system. So for that, let's say the power delivered by this DC voltage source is, let's say, P into E, which is equals to I into E, where I is the current in this circuit and E is the potential difference across the terminals of this DC voltage source. So the total power delivered to the system is equals to I in this case is 4 milliampere, while the potential difference across the terminals of this DC voltage source is 24 volts. So the total power delivered to this system is equals to 96 milliwatt. 96 milliwatt of power is delivered to this system. Now we will find out that how much power is absorbed by each of this component. Now let's say the power absorbed by this first component is, let's say, P1 equals to I S square into R1. So the power absorbed by this first component is the current here in this network is whole square, and the resistance value of the first resistor is 1 kilo ohm. 1 kilo ohm. So the resulting power absorbed by this first component is P1 is equals to 16 milliwatt. So 16 milliwatt of power is absorbed by this first component. Now the power absorbed by this second component is, let's say, P2, and P2 is equals to I square into R2. So the power absorbed by this second component is, the current in this case is 4 milliampere whole square into the resistance value of this second component is 3 kilo ohms. So the resulting power absorbed by this second component is 48 milliwatt. So 48 milliwatt of power is absorbed by this second component. Now the power absorbed by this third component is, let's say, P3, which is equals to I square into R3, because the current is the same in the series combination of resistors. So the power absorbed by the third component is equals to 4 milliampere whole square into, and the resistance value of this third component is 2 kilo ohms. So the resulting power which is absorbed by the third component is equals to 32 milliwatt. So 32 milliwatt of power is absorbed by this third component. Now let's prove this point, which states that the sum of all the power absorbed by any system is equals to the sum of all the power delivered to the system. Now the sum of all the power absorbed by this system is P1 plus P2 plus P3, and the sum of all the power delivered to this system is PE. Now as we derived that P1 is equals to 16 milliwatt, while P2 is equals to 48 milliwatt, plus P3 is equals to 32 milliwatt, and the power delivered to the system is 96 milliwatt. So after calculating this, we get 96 milliwatt is equals to 96 milliwatt. So the power absorbed by the system is equals to the power delivered to the system, which obey the law of conservation of energy. So it's all for today's presentation. If you have any doubt, ask in the comment section. In the upcoming presentation, we'll be discussing some more example about the electrical power in a series combination. So see you in the next one.